Today we'll be working on the following problem. Find an example of a Borel measure mu and the Borel set E on R such that mu of E is positive but strictly less than the infimum of all the mu of F, where F is closed in R and F contains E. Pause the video if you want to work on this problem by yourself. Okay, let's see what our solution is. What is our example? First, we know that for any Borel measure mu on R, a mu is regular, meaning like mu of E is the supremum of all this mu of F, where F is closed, F contains in E, right? For all E, Borel set in R. Okay, notice the difference, right? So this is in the supremum case is F is contained in E, but in the infimum case, F contains E in our problem, right? So so we require this E, the measure greater than 0. Let's just use the Vega measure. Vega measure in R to be our mu. The Vega measure is also a Borel measure, right? On R. And now let's recall the Cantor set. What's called the Cantor's a middle, what's called the middle third set, right? So to construct the Cantor's middle third set, what we do is like you take the closed interval from 0 to 1, and now in the middle you remove a open interval with length 1/3, and then in this remaining two parts in the middle, and then you remove another 1/2 square here, 1/2 square, the open interval with length 1/, and then you continue doing this, right? So now we just want to mimic the exactly same procedure, but in this time let's see, pick some epsilon between 0 and 1. Now from this 0 to 1 in the middle, instead of remove the open interval of length 1/3, we just remove epsilon/3, the length of epsilon/3, and then we continue this. So here would be epsilon/3 square, right? And then here this, and then we continue the same procedure, and then we just let our E to be the union of all this removed open interval, right? So we're uniting all of them. So clearly E is open because it's the countable union of open intervals. What's more important, like exactly the same argument as we did for the Cantor set, right? So E is dense in 0, 1. E is dense, meaning like E closure is exactly 0, 1 open interval, right? So now let's compute the measure of E. So mu of E, because we're using Lebesgue measure, so it's the Lebesgue measure of E. which is easy to see. It's we sum from 0 to infinity, and then 2 to the n over 3 to the n plus 1 epsilon, right? So that's exactly the same computation as we did in the Cantor's middle third set case. So this actually gave us let's say epsilon over 3, which is n from 0 to infinity, 2 over 3 to the power of n. And this is a geometric series. So which is epsilon over 3, 1 divided by 1, this, right? So which is epsilon. So we know the measure of E is epsilon. But in this case, for any F closed in R and F contains E, we have F must contains the closure of E, right? Because F is closed. So the closure of E we know because E is dense in 0, 1, which is the unit interval 0, 1. So for this infimum mu alpha, if we take all the infimum of all this measure of F closed, F contains E, this is what? Because each mu of F, here mu of F is greater than or equal to 1, right? Because it contains the unit interval. So for this infimum, clearly this is 1. But then the mu of E is epsilon, which is strictly greater than epsilon. That's it.